Celeste. Uh, Good afternoon, everyone. First of all, thank you to the organizer of this conference and RK Singh sir for giving me opportunity to present my work. And the title of my topic is Effect of Silane Treatment on Kapok Fiber and the Mechanical Properties of their Reinforced Composites. This work is done under the supervision of Professor Dilip Kumar Biswai. Basically, the work is focused on the fabrication of this nature-derived kapok fiber reinforced composites and the investigation of the silane effect of the silane treatment on the mechanical properties of these composites. So these are the outlines of my presentation. So basically, composite consists of matrix phase and reinforcement phase. The role of the reinforcement is to strengthen the composite, and the role of the matrix is to bind the reinforcement together. There are different kinds of composites are available on the basis of types of matrix and types of reinforcement. Here, my work focused on this thermosetting polymer matrix composites, and on the basis of reinforcement composites are fiber, laminate, and particle type. And here we are focusing on fiber reinforced composites. Basically, fibers are of two types. One is natural fiber, another one is man-made fiber. So these man-made fibers gives more strength to the composites, but these are not biodegradable. So we have to find some sustainable applications, that is natural fibers. These natural fibers also may not attain the properties that meet the properties that is provided by man-made fibers, but it can be used for structural or semi-structural application or to reduce the weight of this polymer composites. So here kapok is a natural seed-based fiber. So I used kapok fiber to fabricate polymer matrix composites. So these kapok is a plant fiber. They have different constituents. These are cellulose, hemicellulose, lignin, pectin, wax, and these fibers are arranged in different layers. So this middle lamellar layer is rich in some wax and some dust particles that makes incompatibility between the fiber and matrix. So we need some treatment to remove these impurities, and to enhance the mechanical properties of these composites we need some modification techniques that modify the fiber structure, and that will help in enhancing the properties of the composites. So the aim is to fabricate kapok fiber reinforced composites. As you can see, these natural fiber reinforced composites have different applications that's already discussed throughout this conference. And to enhance the properties of these composites, we need some surface treatment techniques. There are different kinds of surface treatment techniques are there. Some are physical and some are chemical. So physical techniques like silane treatment, plasma treatment, microwave treatments are there, and some chemical treatments like alkali treatments, acid treatments, or silane treatments are there. So here I focused effect of the I used silane to modify the structure of the fiber. And here you can see that this is a basic structure of a composite, where these fibers are bound together by long polymer chains of the epoxy, and this black color bond represents the cross-linking between the epoxy, and this green color bond represents the cross-linking between the fiber and the epoxy polymer. So to enhance the mechanical properties, we have to enhance the cross-linking between the. We have to introduce some reactive groups that will help in binding between the fiber and matrix. In this way, we can enhance the mechanical properties of these composites. So for fiber treatments, the fibers are first purified using dewatching process. In this dewatching process, the fibers are treated using ethanol and acetone solution. Then these are treated with silane. As you can see, this silane has bifunctional characteristics. This is the hydrolyzed silane. One side is rich with carbon and another side is rich with OH group. As you know, cellulosic fibers are hydrophilic in nature and epoxy is hydrophobic in nature. So this carbon containing side that is hydrophobic in nature, that will react with the epoxide groups of the epoxy, and this OH group that is hydrophilic in nature, that will react with the fibers with the fiber. In this way, this silane acts as a bridge between the fiber and matrix, and that will help in cross-linking between the fiber and matrix. We can link that fiber and matrix chemically, and that will help in enhancing the composite properties. So that is the possible bonding pattern of the silane with the kapok fiber that is proposed here, and that is verified in the subsequent section. So after silane treatments, these kapok fiber reinforced polymer composites are fabricated and cut into the required dimensions as per ASTM standards to investigate the flexural, tensile, and dynamic mechanical properties. We used hand up techniques to fabricate the composites, and these are the composites that we fabricated. These are the samples and the abbreviations that I used here. So before investigating the properties of the composites, first we investigated the properties of those fibers, how this chemical treatments affects the structure of these fibers. So here you can see that first we investigated XRD. Here you can see that there is an extra peak introduced at 6.360 degree. This is due to the silane. Silane has a polymer structure that has, due to that polymer structure, there is one extra peak introduced, and you can see that the crystallinity index increases with increase in silane concentrations, and at around 9% we obtained the highest crystallinity index and crystallite size. These are calculated using Segal's formula and Serre's formula respectively. And so these two, this one represents API spectra. From API spectra, we can see that there is some functional group changes of the fiber. As you can see that it's 470 and 963. There are two peaks are introduced. That is due to the SiO-C linkage of the silanes and the fiber. And there is one peak 819 and 696. This is due to the SiO-Si linkage, that is due to the cell polymerized silanes. Then also you can see that that at 3358, this is due to the OH group. With increasing silane concentrations, this transmittance percentage decreases. That is due to the removal of the OH group. This OH group that makes incompatibility between the fiber and matrix at the interface. So to enhance the compatibility, these are removed from the fiber structure. That will help in better linking between the fiber and matrix at the interface. From the FPSM, you can see that in case of in figure A, you can see that is the raw fiber, and after silane treatment, you can see that the silanes are modified the fiber structure. So this will help in better mechanical interlocking between the fibers. This silane not only modified the chemically, it also modified physically. These are the mechanical properties of this fiber reinforced composites. As you can see that in case of raw fiber, the flexural strength is found to be around 29 megapascal, and after silane treatment at around 9% silane treated on the kapok fiber reinforced composites, you can see that flexural strength is around 60, which is 2 times more. Similarly, we can observe tensile strength also increases after silane treatment, and further at 11%. That is decreases, which is due to the degradation of the polymer chains of the fiber. And this is the flexural stress strain curve, and that is the tensile stress strain curve. In case of raw fiber, we can see that there is a progressive failure we observe, and after with increase in silane concentrations, this shows catastrophic failure. So this is due to the good interfacial interlocking between the fiber and matrix. But in case of tensile loading, all the composites shows catastrophic failure. This is due to the participation of all the fibers during mechanical loading. However, the strain percentage decreases with increase in silane concentration, and tensile strength increases. This is due to the good bonding between the fiber and matrix. These are the interfacial properties of this fiber reinforced composites. As you can see, as figure 1 is this is the raw kapok fiber reinforced composites. Due to the poor interfacial properties, there is some debonding between the fiber and matrix, and fiber pull out may take place. However, in case of 9% silane treated composites, we can see that fiber breaking at the interface instead of fiber pull out. So this is due to the good bonding between the fiber and matrix. But however, in case of 11% silane treated fiber reinforced composites, these silanes degrade the polymer chains of the cellulose. That's why there is some rupture in this interface observed. That's why the mechanical properties of these composites also decreased. This is the dynamic and mechanical properties of those composites. As you can see that in case of raw fiber treated composites, we found the storage modulus is around at low temperature region is around 3000 megapascal, and at 9% silane treated composites we found that 6000 megapascal, and also we can observe from figure B that the glass transition temperature shifted towards the higher temperature side, around shifted by 10 degree, which is due to the good bonding and binding. This glass transition temperature increases. This makes the composite also thermally more stable. These are the water absorption properties of this composites. As you can see that this is measured using as per the ASTM standards 570. As you can see that this measured up to 12 days. As you can see that in case of raw fiber, the water absorption percentage, maximum water absorption percentage is around 8%, and in case of silane treated composites, the minimum water absorption maximum water absorption percentage observed is around 4%, which is 50% lower than those composites. So this makes this silane treatment not only stabilize the mechanical properties, it also decreases the water absorption properties of those composites. So this makes this kapok fiber for the application of lightweight composites. And, this is the summary of my work, where kapok fiber reinforced composites are fabricated using hand layout techniques. The structural modifications are observed through XRD, FTR, and FPSM spectra, and we obtained that the silane treatment enhances the flexural strength by 132%, tensile strength by 12% respectively. So these are my references. So thank you everyone for being here.
Additional point is much So how much you modified your fiber on the lab scale, and what was the scale? 10 gram to
Sorry, sir?
You modified your fiber using silane. So what is